Have you ever just looked at the world around you and wondered why some things just seem to happen? All on their own, without any obvious push or pull. Well, today, we're going to dive deep into the science behind that very idea, spontaneity.
I mean, think about it. A geyser just erupting, shooting steam and water way up into the sky. A waterfall just constantly, relentlessly flowing down. Nobody's pushing a button to make these things work. They just happen. So what's the fundamental rule of nature that's calling the shots for these one-way events?
You see it everywhere. These processes all have a natural kind of preferred direction. Water doesn't decide to flow uphill by itself. Rust doesn't magically turn back into shiny new iron. And a puddle of water on your kitchen counter isn't going to spontaneously freeze on a warm day. It really is like nature has a bunch of one-way streets.
Okay, so to really get our heads around this, we need to get a little more specific with our language. In science, we basically split all processes into two big categories, spontaneous and non-spontaneous. Let's break down what those terms really mean.
So a spontaneous process is one that'll happen all on its own, as long as the conditions are right. The perfect example, an ice cube melting at room temperature. You just put it there and it happens. You don't have to do anything to it. The process just unfolds naturally.
On the flip side, you've got a non-spontaneous process. This will absolutely not happen unless you're constantly feeding it energy. You want that water to go uphill? Well, you're going to need a pump, and you're going to need to keep that pump running. It's that continuous input of energy that drives the whole thing. And this right here, this shows a fundamental rule of the universe. If a process is spontaneous in one direction, like our ice cube melting in a warm room, then the reverse process, water freezing in that exact same room, is always going to be non-spontaneous. They're literally two sides of the same coin.
Okay, let's pause here, because we're about to hit a really common misconception. When most people hear the word spontaneous, they immediately think instantaneous or super fast. But in the world of thermodynamics, nope, that's not what it means at all.
This chart is the perfect way to see why. Just look at this. Both of these isotopes, technetium-99m and uranium-238, undergo spontaneous radioactive decay. But their speeds? They are worlds apart. Technetium has a half-life of just about 6 hours. Uranium-238, on the other hand, has a half-life of over 4 billion years. Both processes happen on their own, but one is incomprehensibly slower than the other.
All right, now for an even more mind-bending example. You've heard the saying, diamonds are forever, right? Well, science has a little something to say about that.
You might want to sit down for this one. Believe it or not, under the normal, everyday conditions here on Earth, the process of a diamond turning into graphite, yep, the same black stuff you find in your pencil, is actually thermodynamically spontaneous. Nature wants it to happen.
And this brings us to a super important distinction. Thermodynamically, that diamond is unstable. It's kind of like a perfectly balanced boulder sitting at the top of a very long, gentle slope. It wants to roll down and become graphite, but kinetically, it's stable. It needs a huge energy push to even get it started, so the rate of that change is so ridiculously slow that, for all practical purposes, your diamond is, in fact, forever.
So, if spontaneity isn't about speed, then what is the real driving force? What makes things want to happen in the first place? Well, it turns out it's not always about lowering energy. Let's dig into the true principle at play here.
To figure this out, we're going to use a classic thought experiment. So just picture this. You've got two glass flasks, and they're connected by a little tube that has a valve on it. So at the start, all of our gas is crammed into one flask, and the other one is a total vacuum. Now what happens when you open the valve? Whoosh! The gas spontaneously expands to fill both flasks evenly. But here's the absolute kicker. No energy was exchanged with the outside. The total energy of the gas is exactly the same as when we started.
So if the energy stayed the same, what changed? The distribution of the matter. The gas molecules went from being packed into one little space to being spread out or dispersed across twice the volume. This fundamental drive toward a more spread out, more disordered state is a key reason spontaneous processes happen.
And guess what? This exact same principle applies to energy too. Let's imagine you take a hot block of metal and place it right next to a cold one.
We all know what happens next, right? Heat spontaneously flows from the hot object to the cold one until they both reach the same temperature. It never, ever goes the other way on its own.
And just like with the gas in the flasks, if you look at the whole two-block system, no energy was created or destroyed. It was just redistributed. It went from being all concentrated in one object to being spread out or dispersed more uniformly across both of them.
This fundamental idea that spontaneous processes happen because they increase the dispersal of matter and energy is everywhere you look. Let's check out a few more examples in action.
You see this all the time. Think about sublimation. That's when a solid, like dry ice, turns directly into a gas. Or diffusion, like when a single drop of food coloring slowly spreads out to color a whole glass of water. In both cases, the result is the same. Matter becomes way more spread out. These are processes that dramatically increase dispersal.
This chart really shows the difference. Look at that huge bar for sublimation. When a solid becomes a gas, the molecules just fly apart and spread out immensely. Diffusion also causes a big increase in dispersal. But now look at the bar for condensation. When a gas turns into a liquid, the molecules actually get closer together, decreasing their dispersal. That's why condensation only happens spontaneously under very specific conditions.
So whether we're talking about gas spreading out in a container, heat flowing from a hot object to a cold one, or a drop of dye mixing into water, the big takeaway here is the same. The real driving force behind why things just happen is this relentless tendency of the universe to move toward a more spread out, more uniform state. This drive towards dispersal is so important, scientists actually gave it a name, entropy. And the idea that the total entropy of the universe is always increasing is the famous second law of thermodynamics.
And that leaves us with one final, absolutely massive question to chew on. If every single spontaneous process is pushing the universe towards a more spread out, more uniform state, what's the ultimate endgame? What happens when everything is as spread out and mixed up as it can possibly be? It's a question that really gets you thinking about the ultimate fate of the universe itself. Something to ponder.